So in the previous lecture, we were discussing about inner product spaces. So I need to zoom it, I think. I hope you can see the board properly. Now, is this fine? I think, yes. Not right now. So let me zoom it properly. Okay, that's fine, I think. So inner product, we were discussing what are inner products. Inner products are basically generalization of the dot product in R2 and R3. So now inner products are basically defined for inner products. Inner products are defined for elements in Rn. So in general, we define inner product for any two vectors, for example, uv or xy, maybe xy are two vectors in Rn. Then the x can be written as, I hope you know, x1, x2, so on, xn. And y is defined by y1, y2, so on, yn. So then we define the dot product x dot y. In general, we are going to change its notation. And now we are going to denote it by x, comma, y, and this is less than greater than brackets. Now, what is this? It is basically, we multiply the corresponding components of these vectors and add them. So it's not properly. What happened to this? Properly visible. No, I hope it is visible now. Now, what is this? So how do we define dot products? X1, Y1 plus X2, Y2 plus so on plus Xn, Yn. So this was basically the definition of dot product. And how can we connect dot product with the norms we had discussed? If we define a dot product of any vector with itself, then it can be written as norm of x squared. So this was an important relation we discussed in the previous lecture. We have also discussed some of the properties of the inner product, that inner product of any vector, any two vectors is commutative, means x inner product with y is equal to y in inner product with x. And couple of more properties we had discussed. You can see my previous lecture for the details of those properties. Now, we are going to define angle between two vectors. Angle between two vectors in Rn. In Rn. So, for example, we have the same vectors x and y. Then how do we define the angle between these two vectors? For example, if we have two vectors, this one and this one, this is x vector and this is y vector, and these two vectors are basically in Rn. Then the angle is what? Angle, let me call it theta. Theta is the angle between these two vectors. Then angle is basically, you might have studied in your earlier classes that the dot product between two vectors is in general is what? It is basically mod of x into mod of y times cosine of theta. You might have studied this thing. You might have seen this relationship where this mod of x is what? It is the length of that vector in R2 or R3. This mod of y is basically length. Now we are going to extend these notations in inner products and norms. So this x dot y will now be denoted by x comma y, and x, this length of x mod is defined now norm of x, and now this one is norm of y times cosine of theta. So this is basically the generalization of that that expression in Rn. Now, if we want to find the value of theta here, we can solve it. So cosine of theta is what? It is the inner product of x, y divided by the norm of x times norm of y. So now this expression can give us the theta, which is what? We take this cosine on the other side. So we can find theta equal to cosine inverse of this whole thing. Inner product of xy divided by x norm and y norm. If you have any question, you can ask me. So theta can be calculated from this expression. And remember that this theta is always between 0 and pi. Okay. If you have theta greater than pi, then it would be basically this theta is what? It is counterclockwise rotation. Okay. Counterclockwise angle, you can say that. So this must be between 0 and pi. Okay. If you have some kind of angle greater than pi, for example, 3 pi by 2, then that would be equivalent to by theta between 0 to pi, but you can take the clockwise rotation of the theta, and you can still put that angle between 0 and pi. I hope you get it. If you have any question, you can ask me. There's a question in the chat window. So can you please repeat the bit about inner products? I joined a bit late. I did not explain much about inner product. Inner products, basically, the initial discussion was done in the previous lecture. I just gave the definition of inner product. Inner product is basically the generalization of the dot product in Rn. Dot product you define, you have already studied it for R2 and R3 spaces. Now we are going to generalize that concept of dot product in Rn. And now in Rn, in general, we call them inner product, not the dot product anymore. So this is how we define the angle between two vectors in Rn. For example, if you want to compute the angle between maybe two vectors, let the vectors be, yes, this one. Here we are given two angles, two vectors. For example, u is a given vector, which is 1, negative under root 2, 1, and the v vector is 2 square root 2, 0, and negative 2 square root 2. So find the angle between these two vectors. Find theta. Okay. So what do? We have that expression, cosine of theta is equal to inner product of xy and norm of x, norm of y. So we need to compute first inner product between u and v. So what is this? It is basically component, the sum of the products of each component. Okay. So this will be 1 times 2 under root 2 plus negative under root 2 times 0 plus 1 times negative 2 under root 2. So this is the dot product or the inner product. That becomes 2 under root 2, 0, and this one is negative 2 under root 2, which is 0. So the dot product is 0. Now, what is the norm of u? Norm of u is the sum of square of its components, this one plus 1 square. So this would be 2, and then 2, 4. 4 square root 2 is 2. And then now v vector, norm of v vector is 2 square root 2 square plus 0 square plus negative 2 under 2 whole square root. So this would be 4 2s are 8, 4 2s are 8, 16. So the square root of 16 is 4. Now, as we know that the cosine of theta is what? It is u inner product u in v divided by norm of u times norm of v. So as the numerator is 0, so whatever we have in the denominator, it will be 0. So cosine of theta is 0, and theta is what? It is cosine inverse of 0, and it is pi by 2. So from here, what do we? What is the question? No. So the theta is pi by 2. What does it mean? These two vectors are perpendicular to each other. Okay. So whenever from here, you can observe that whenever we have 0 here, the dot product is 0. Sorry, whenever we have 0 here, it means these two vectors are orthogonal. Okay. So we obtain a result from here. We can define orthogonal vectors. If the inner product of any two vectors is 0, then u is orthogonal to v. Okay, this is the definition of orthogonal vectors. Means two vectors are perpendicular to each other or orthogonal to each other if the dot product or inner product is 0. So keep this thing in your mind. If you have any question, you can ask me.
Yes, sir. I had a question.
GG.
Sir, not about the topic, but I just wanted to ask if there was a test on this Wednesday.
Oh. You want?
We don't?
Do you want a test on this Wednesday or not?
No, sir. पिछले हफ्ते तो मिड दिया है.
चलो ठीक है. इस हफ्ते नहीं लेंगे फिर. Next week ले लेते हैं.
Thank you,
Happy?
सर इस हफ्ते भी बहुत सारे मिड्स हैं हमारे. अगले हफ्ते सब ब्रेक दे दें.
चलें ठीक है. Next week लेंगे हम. ठीक है. Another example from the inner product, which might give you some clear understanding of inner products. We are going to use a couple of properties in this example, how to use the properties of inner product. For example, if we are given, let u and v, there are two vectors in Rn. We don't know the dimension of Rn. We are given these things. U dot u is 9, u dot v is -7, and v dot v is 16. So we need to compute 3u minus v dot u minus 3v. So I hope you can do it. With the help of the property we discussed at the end of the previous lecture. What was that property? That was the generalization of the distributivity property of inner product. So this inner product, or we can write it in this way, 3u minus v, 3u minus v, comma u minus 3v, this one. So I told you, how can we write this inner product? You take the inner product of first vector with first, and then first vector with second. Okay, how do we write it? 3u inner product u with the first vector, and then 3u with the 3v with the negative here. So we have negative 3u comma 3v. So these are the inner product with the first vector. Now we are going to take the inner product with respect to the second vector. First, we take the inner product of v with u, and then of v with 3v. take care of these signs. Now we have a negative sign with V. So you can write here plus negative V U plus negative V comma negative 3V. So this is how we can expand this inner product I told you in the previous lecture. You can see that property in order to understand this. Now, we are going to use the constant multiple kind of property of the inner product. We can take constant out of this inner product. So we can write 3 times U inner product U, and then negative a 3 out from here and 3 out from here as well. So it becomes 3 times 3. It becomes 9 inner product UV. Okay. And then this one, you can take negative outside, and then VU is commutative because the inner product is commutative. So we can write it U comma V. So this becomes negative U comma V. We have used here the commutative property of inner product plus plus. So a negative sign out from here, negative, and negative 3 from here. So it becomes negative 1, negative 3, which is positive 3. So it becomes VV. Now we know that this U inner product U is, it is what U dot U is, U in fact U inner product U. So it is 9, U inner product V is -7, V dot V is 16. So we can insert the values here and get the answer. U dot V is 9, and negative 9 times negative 7, negative U dot V is again negative 7 plus 3 times 16. So after solving this, you can get the answer. I hope you got it. If you have any question, you can ask me. Another important definition of the inner product is the projection, or you can say projections of a vector. Or orthogonal projections. Let me, wait, I'm gonna change the board. This one is the second one. I hope you can see it. I think camera is a bit ahead. Wait for a minute. Let me adjust it. I don't know what happened to this thing. I think it's better now. Yes. Now, the projection theorem is a very important theorem here in inner product, which we use in many concepts of the linear algebra and many other courses. It's a projection theorem. In fact, graphically, what does it mean, the projection theorem? If we have two vectors, G with
सर कुछ बच्चे क्लास ज्वाइन करने की कोशिश कर रहे हैं, they are unable to join, किसी ब्रेकआउट रूम में जा रहे हैं, वो उसी लिंक से
people are not able to join the meeting. Start again. So projection theorem, in fact, tells us that if we have two vectors, for example, U and V, not like that. Let me use the same notation. We have a vector U and another vector, maybe V. Okay. Then the components of U can be computed along V and perpendicular to V in order to make a projection of U onto V, or you can say a kind of right angle triangle. We have a U vector, then the component of U along V, sometimes we need it. The component of U along V is what? It is U dot V, means inner product of U and V. Okay, and this is what? No. Sorry. It is K times V, I think. Yes. Yes. If we try to write U in terms of W1 plus W2, so let me. If we have two vectors U and V, then U can be uniquely written as W1 plus W2. This is what projection theorem tells us. If we have two vectors U and V, then U can be uniquely written as sum of two vectors W1 and W2, where W1 is what? Where W1 is K times V vector. And this is what? This is the vector component of U along V. And this is what it is, some vector which is scaled. It is a scaled vector obtained from V. Okay. Now this is called vector component of U along V. And this is what the dot product tells us as well. We'll see it later on. So any vector U can be uniquely written as the sum of two vectors, W1 and W2, where W1 is what? K times V, where K times V, or you can say the W1 is what? W1 is a vector component of U along V. And this vector is a scaled vector V. Either it would become longer than the normal V or be shorter. It depends on the value of K. And the second vector, W2, is a vector which is the projection of U onto this V vector. This is your W2 vector, and this green one is your W1 vector. So this is what projection theorem tells us. If we have two vectors, U and V, then we can find the components of U along V and orthogonal to V. Okay, so in short, U can be uniquely expressed as vector component of U along V plus vector component of U orthogonal to V, orthogonal or perpendicular, orthogonal to V. So every vector, if we have a vector U and another vector V, then U or V, vice versa, we can write in both ways. U can be uniquely expressed as the sum of two vectors. The one is the vector component of U along V, and the other is the vector component of U perpendicular to V. This is what projection theorem tells us. Okay. Now we know the expression for W1. The W1 is what? It is a scalar multiple of V. Okay. Now, what is W2? We don't know. We need to find what would be the form of our W2. And also, we don't know what is the value of K here. We need to know the value k here. So now, if we want to express u as a sum of two vectors, then we can write it in the form of w1 plus w2. And we know that w1 is a scalar multiple of v. We don't know what is w2, what is the form of a w2. And also, we don't know the value of k here, how to find this k. So now we are going to find two things. The first one is k, the value of k, and the other one is the expression for w2. We need these two things in order to find the vector component of u along v and the vector component of u perpendicular to v. So how to find them? In order to find the k, what do we do here? We have this u. We take the dot product of u with v, because we only know two vectors, u and v. So in order to find k and w2, we can only use these two vectors, u and v. So what we do here, we take the dot product of u with v on both sides. Here we have w1 plus w2 dot v. Now, by using distributive property of the inner products, because this is what? This is the inner product. Now, this can be written as w1. We know that w1 is what? It is k times v. So we write here k times v and dot product with v. K times v dot v plus w2 dot v. Okay. Now here we have the same u dot v. Now we know that w2 is orthogonal to v. We have defined w2 in a way that w2 is orthogonal to v. So if w2 is orthogonal to v, then this dot product will become 0. I hope you got it. Now if this dot product is 0, then we can find the value of k from here. What is this? V dot v is norm of v squared. We can divide this norm of v squared on the other side and obtain the value of k. And this would be, so the value of k would be what? It is the inner product of u with v divided by norm of v squared. So we can find that value of k by using this expression. Because u is known, v is known, we can compute the inner product of u and v. We can compute the norm of v squared. Okay. Now, we need to find the expression for w2 now. As we know that u is what? U is w1 plus w2 vector. And we know that w1 is k times v plus w2 u. Now, we know that k is what? K is inner product of u v divided by norm of v square times v. Okay, now this is basically a scalar. This is a scalar, remember this. So plus w2, and this is here we have u. Now we need to find w2. We know this thing, we know this thing. So the expression for w2 is what? It is nothing but u minus inner product of uv divided by norm of v squared times v. Okay, this is the times v, scalar multiple of v, not the dot product. Okay, there's a difference between dot product and scalar multiple of a vector. Okay, let me write it clearly. So this is okay. Now we know that this is w2. We know it. All the things here in w2 are known. We know vector u, we know vector v. We can compute inner product of uv, and we can compute norm of v squared. Now this is basically the orthogonal component of u onto v. Okay. Now these things we can write them we can write basically in a more sophisticated kind of notation. How do we denote them? The first vector, which is the W1, it is basically denoted by projection of U onto V. Okay, it's basically along V. Okay, which is U comma V inner product divided by norm of V square times V. Okay, this is the projection. This is what it is, the vector component of U along V, and it is what it is, vector component of U along V, and we denote it by projection of U onto V. Okay. Now, how do we define W2? W2 vector is denoted by, if we denote W1 by this, then W2 is in fact what? It is U minus projection of U along V. Okay, and this is what it is, nothing but U minus inner product of U V divided by norm of V square times V. This is how we denote these two vectors. Okay, and they are basically projections. Ji, beta, ji, ji.
Are the equations always standard, or will they keep differing with different things?
Kindly speak a bit loud.
Will these equations always be standard, या वो different vectors के साथ we'll have different equations for W1 and W2?
No, these are standard. We never assume the form of a vector, or we never taken a particular form of a vector. These are for all vectors belonging to Rn. Okay, where U and V, they belongs to Rn. Okay, these two vectors for all U V belongs to Rn. The U V could be any two vectors. Okay. Now we have a vector component of U along some other vector V, and we can find the vector component of U, which is perpendicular to some other vector V by using these two expressions. Where what is W1? W1 is nothing but projection of U along V, and you know the expression of this thing, and plus the other thing is U minus projection of U along V. These are two vectors. This is the expression for W1. It is basically U can be written as this, which is W1, and this, which is W2. So this is your W1, and this whole thing is W2. Now, this is what projection theorem tells us. Now, let's have an example of this thing. Let U and V be two given vectors. Let U is this vector, 2, -1, 3, and V is 4, -1, 2. Okay. In order to save the space, some people write these vectors in the row vectors form just to save the space, but technically we should write them in a column vectors. Now we need to find here the vector component of U along V and orthogonal to V. Okay, so how to find it? In order to find projection of U onto V, we need what? We need inner product of U V divided by norm of V whole square times V. Okay. So in order to find this, what do we need? We need dot product of UV, and it is what? You multiply the respective components and add them. So this is 8 plus 1 plus 6. Okay, and this is 15. And now you can find the norm of V square. Now V square is the what? 16 plus 1, 17, 4, 21. Okay. That's it. Now the projection of U along V is what? It is the dot product 15 divided by what? 21 times V. Now what is V? V is 4, negative 1, 2. Okay. Now you multiply this 15 by 21 inside, and then you can get this vector having 3 components. I hope you can do it. Similarly, in order to find the projection of U onto V, or the orthogonal projection, the other vector, you can just compute that vector by subtracting this vector from U. So U minus projection of U onto V. So this one, which is the orthogonal or the perpendicular onto V, you can compute this by subtracting this vector from U vector. I hope you can do it. If you have any question, you can ask me. These are the projection of U along V and orthogonal to V. These are very important concepts which we'll use very frequently in the upcoming concepts.
सर ये नेगेटिव नहीं होगा साइन बीच में?
हाँ बे, हाँ नेगेटिव ही होगा. Thank you. This one. So these are some of the important concepts related to projections. If you have any question, you can ask me. You can see it for a couple of minutes if you want to. Then you can ask me any question. Do you want? Look at these things for 1 minute. Meanwhile, I'm gonna erase things on the other board. And then if you have any question, you can ask me. So, do you have any question? Otherwise, we are going to discuss another important thing in inner products. So, this one.
सर
G.
सर ये जो KV है ये U के इक्वल है या W1 के इक्वल है?
K times V is equal to W1, which is the vector component of U along V.
ठीक है सर.
Okay, now we are going to discuss a very few important properties related to the norms and inner products. The first property is or you can say inequalities, important inequalities. Okay. The first one is Cauchy-Schwarz inequality. CAU, let me write it clearly. CAU-CHY, Cauchy, SCHWARTZ, Cauchy-Schwarz inequality. Okay. What does this Cauchy-Schwarz inequality tells us? That for all u v belongs to Rn, we have this expression that is the absolute value of u comma v inner product. Okay, absolute value. This thing is what? Absolute value. It's not the length. Okay. Absolute value of inner product of uv is always less than or equal to the norm of u times norm of v. This is what Cauchy-Schwarz inequality tells us. Because the inner product is what? Inner product is a single real number. When you take the dot product of two vectors, what do we get? We get a single real number. Remember this. I hope you know it. Why this is not okay? No, it's fine. You know that the dot product of two numbers is a single real number. That single real number could be positive or negative. Okay. Now that's why we put an absolute sign here, or you can write here this thing as u dot v. Absolute value is less than or equal to norm of u times norm of v. This is what Cauchy-Schwarz inequality tells us. Now, in order to prove this property, let's discuss different cases. For example, the first case is if either of u or v, if they are is 0. Okay, for example, if u is 0, then obviously this inequality will be satisfied. 0 vector with any vector, if you take the dot product, this is always 0, and norm of u will always be 0, whatever we have here. So the equality holds. Okay. If none of these two vectors is 0, then how to prove this? How to prove it? In order to prove it, we consider what do we consider? Tu plus v norm square. This is always greater than or equal to 0. We start with this expression because if we don't assume this expression, we cannot prove it. Okay. In mathematics, sometimes in order to prove a certain result, you have to start with somewhere. So what's this thing? Can you see the complete board?
Yes,
Because
sir.
मेरे लैपटॉप में मेरे जो है ना वो थोड़ा सा डिफरेंट नजर आ रहा है और प्रोजेक्टर में डिफरेंट नजर आ रहा है. I don't know what's happening. So now we start with this expression. If we don't start with this expression, we cannot prove it. Okay, you have to remember this expression, as I did. So in order to prove Cauchy-Schwarz inequality, you have to start with this expression. Otherwise, you cannot. Where t is some real number. Okay, you can say that t belongs to R. T is some variable. Okay, t is some variable which is some kind of no, t might not belongs to R. T is some variable, this parameter you can say. It can take, we'll discuss later on what kind of values it can take. So if we know that norm of anything, norm of any vector is always greater than or equal to 0, unless this vector is itself 0. So on the safe side, we say that the norm of this thing, norm square of this thing is always positive, greater than or equal to 0. Now we know that this norm of any vector tu plus v, it can be written as what inner product of this vector with itself using the properties of norm and inner product. Let me see, I have written the correct expression. Yes. How can we write this? Because we know that norm of u whole square is what? It is inner product of u with itself. So this is this. We had discussed this thing previously when I started this lecture. So now this whole thing is greater than or equal to 0. I put it greater than 0. Now using that distributivity property of inner product, I can expand this and I can write this thing as t square uu plus tv and vt. It becomes 2 times t uv and plus plus v inner product v. So this is what we have obtained. Now further, I can simplify this into, let me write on the other board maybe. I can write this thing tu plus v norm square is equal to t square times norm of u square plus 2 times uv plus norm of v square. Okay, this thing. यहाँ पे t भी आएगा. We have a t here, 2t. Okay. Now, if we assume that this is something a t square, where a is what? It's norm of u square, plus bt, where b is what? 2 times inner product of uv, plus c, where c is what? v norm square. Okay. Where you can put here a is what? It is norm of u square. B is what? 2 times u v, and c is what? C is norm of v square. This is what. Now, what is this now? This whole thing is greater than or equal to 0. As well, this whole thing is greater than 0. This comes from the previous discussion. Now, this is what? This is a quadratic polynomial which is always greater than or equal to 0. It has, then what does it mean? If a polynomial of degree 2, if a quadratic polynomial is always greater than or equal to 0, because the coefficient of t square is positive, because a is what? Norm of u square. This is always positive. C is always positive, and this b must also be positive. Otherwise, you cannot have this always greater than or equal to 0. It is possible. So if a quadratic polynomial is always positive, then it cannot have real roots. Okay. So the roots of this polynomial must either be 0 or complex numbers. Roots of this polynomial must be 0 or complex numbers. If a quadratic polynomial has roots as a complex number, then what we can write? Its discriminant. Discriminant is what? B square minus 4ac is always less than or equal to 0. I hope you get it. This is what you call the discriminant of a polynomial. And where do this discriminant come from? When you try to find the roots of this polynomial, you have a quadratic formula, which is minus b plus minus square root b square minus 4ac divided by 2a. This is how we can find the roots of a quadratic polynomial. So this thing here is what it is called the discriminant of that polynomial. Now, if this thing is less than or equal to 0, then you might have either real roots. If this is 0, then you have real roots. You have same roots. Okay. If this is the thing b square minus 4ac, which is inside this square root sign, if this is less than 0, then you must have complex roots. Okay. So because this polynomial is always positive, also greater than or equal to 0, then this polynomial must have either real roots only, the same roots, repeated roots, or the complex roots. So we must have this thing less than or equal to 0. So taking square on both sides, we can write b square minus 4ac less than or equal to 0, and b square is less than or equal to 4ac. Now, you can put the value of b, a, and c here in this expression. What do we obtain? We obtain b square is what? 2 to square 4, and uv inner product, you can say square, okay? This whole square is less than or equal to 4 AC. What is A? It is norm of U square, and C is what? Norm of V square. Now you can cancel this 4 out of this, and then taking square root on both sides, you can obtain that U dot V mod. Okay, because whenever you take square root here, you have to put a mod here, because you know that square root of x square is what? It is the absolute value of x. So using this identity, we can write the square root of this thing is equal to this, and less than or equal to norm of u times norm of v, which is the required Cauchy-Schwarz inequality. I hope you got it. If you have any question, you can ask me.
Sir, why does the quadratic formula need to have non-real roots?
Because it's always positive.
Sir, real roots नहीं हो सकते.
Huh? Real roots होंगे, real होंगे. If this is equal to 0, then you have repeated real roots.
Okay.
Repeated real roots, you got it? या तो roots 1 1 होंगे, 2 2 होंगे, या फिर क्या होंगे? Complex होंगे. So for example, if you can try this, if you have x squared plus x plus 1, if this is always greater than 0, greater than or equal to 0, then यहाँ पे you can take that for all x belongs to 0 to infinity. Okay, if this is the domain of x, can this polynomial have a negative value?
No.
No? Then try to find the root of this polynomial, roots of this polynomial. What would be the roots? X is equal to -1 plus minus square root of 1 minus 4ac, 4a into c, so divided by 2 into 1. So what are the roots? Plus minus, what do you have here? -3 divided by 2, 1. 2 into 1, 2. So if this is less than 0, then here you must have complex roots. Okay?
Yeah, thank you.
Okay, take it. So this was the Cauchy-Schwarz inequality. Now we are going to prove another inequality, which is also equally important. But this uses the Cauchy-Schwarz inequality in order to prove that property, and this is called triangular inequality. And the triangular inequality for vectors in Rn. This is what? It is the triangular inequality. What is triangular inequality? I hope you know it. In your earlier classes, you might have seen it. If you have any two vectors, u plus v belongs to Rn. In R2, you know it, this is what? If you have any triangle, it might not be, the first vector is this, and the second vector is this. This is your u vector, and this is your v vector. And you obtain another vector, which is the sum of these two vectors, this one. Okay, what is this? This is the sum of u and v. So this is u plus v. What does this triangle inequality tells us? That the length of any side of this triangle is, this is the length of this bigger side of this triangle is always less than or equal to the sum of lengths of other two sides. Okay. So what does this triangle inequality tells us? In any triangle, the length of one side is always less than or equal to the sum of the lengths of other two sides. You can choose any one side. Okay. So this is the bigger side. So we say here that the length of this side is always less than or equal to the sum of this side plus the length of this side. This is what triangle inequality tells us. Now, how to prove it? How to prove? We start with this left-hand side, this thing, and we assume that consider norm of u plus v. This is always greater than or equal to 0. Okay, you know it. Norm of any vector is always positive. So now by using the expression of inner product, we can write u plus v. Norm square is equal to inner product of u plus v, comma u plus v. With the same logic we have used in proving the Cauchy-Schwarz inequality. Now I'm going to explain this by using distributive property of the inner product, and I can write u plus 2 times u v plus v v. Okay, and now this is what? This is nothing but u norm square plus 2 times u v plus v norm square. Okay, and this is what? U plus v square. Now I'm going to take absolute value on both sides because this is a number, this is a real number, this is always positive, this is a real number, this is again a real number, it can be negative or positive, this is again a real number. Now you know that absolute value property of two numbers, sum of two numbers. What is that absolute value property? What is that? The sum of absolute of sum of two real numbers is less than or equal to the sum of their individual absolute values. This is absolute value property. Okay. Now we are going to use absolute value property here, and we are going to take absolute values here and here on both sides. Okay. Now this is already a positive number. It will not affect it. The absolute value of a positive number is always a positive number. So we are going to write this thing same as above. Let me write it here. So this thing remains same. Now we are going to expand this. This is what? A plus B plus C. There are three numbers. So we are going to expand this absolute value property, open this absolute, and we obtain here, this is less than or equal to absolute of this thing, absolute value of this thing, and plus absolute value of this thing. Iska absolute value, it will remain same. Why? Because this is already a positive number. Iska absolute, it will remain same because it is a positive real number, because it's a norm square. But this might be a negative real number because it's the inner product. Inner product of two vectors could be positive or negative. So we have to take care of this middle term. So what do we obtain here? U norm of u square plus 2 times mod of uv inner product plus v norm square. Okay. Now here, what is this? This is the u dot v absolute value. U dot v absolute value is what? this is what u dot v, absolute value is less or equal to norm of u times norm of v. And where does this come from? Anyone? Can anyone tell me?
And the Cauchy Schwarz inequality.
Yes, we can write this thing by using Cauchy-Schwarz inequality, and we can further write this thing is less than or equal to this. So this expression now has become norm of u squared plus 2 times norm of u times norm of v plus norm of v whole square. Now this becomes now what? This is equal to norm of u squared, sorry, not squared, norm of u plus norm of v whole square. Because this is a square plus 2ab plus b square. Now taking square root on both sides, what do we obtain? Norm of u plus v is less or equal to norm of u plus norm of v. This is what, this is the required triangular inequality. I hope you get it. If you have any question, you can ask me. You can have a look at this proof. If you have any confusion, you can ask me. So if you don't have any question, we are going to discuss a special case of this inequality. A special case. In the start of this inequality, we assume that we have any triangle, okay? This triangle could be anything. This one is u, this one is v, and this is u plus v, okay? Now, what if this triangle is, what if this triangle is a right angle triangle? Right angle triangle. In that case, we'll have this vector, and this vector. This is your u plus v, and this is u, this is v. Now, in this case, this angle will be a 90-degree angle. If this angle is 90-degree angle, then what happens? Then u dot v is 0. Because they are perpendicular to each other. They are orthogonal to each other. We have already discussed that if two vectors are orthogonal, then the dot product must be 0. If the dot product is 0, then we don't need to put here in this inequality, we don't need to use the Cauchy-Schwarz inequality. We don't need to use the Cauchy-Schwarz inequality. This is equal to this, and this inner product is 0. And what do we obtain? We obtain u square plus v square is equal to u norm square plus v norm square. And what is this? If we assume that this is c, this is a, this is b, sorry, c square, a square, b square, plus equal to. Now, what is this? This is a generalization of Pythagoras theorem. This is the generalization of Pythagoras theorem in Rn, because u and v belongs to basically Rn. I hope you get it. If you have any question, you can ask me. This is the generalization of Pythagoras theorem in Rn. This equality. If you have any question, you can ask me. No question? Okay, that's great. Let me tell you a couple of more properties, and then we'll finish this topic of inner product, and we'll move towards the spanning of a set. There is another inequality which is called equation, parallelogram equation. And this is what, for all uv, two vectors belonging to Rn, we have this thing. U plus v norm square plus u minus v norm square is equal to 2 times norm of u square plus norm of v square. This is called parallelogram equation in Rn. You can easily prove it. It's very easy. You just look at the proof of this equality. I hope you would understand immediately. Remember this property. This will be used in the subsequent topics. Another property, which is basically the same kind of thing. Now, this inequality basically involves what? It involves the norms of vectors only. Another property, you can say that is a theorem. It doesn't have any name, but for all uv belongs to Rn, I don't know exactly what's its name. Then we need to prove that the inner product of u and v is what? It is 1/4 times u plus v whole square minus u minus v whole square. Okay, it is basically just the special case of this property. If you put a positive here and you have a negative here and positive here, so when you take the square, you'll have 2 uv negative with negative sign. Here you have 2 uv, 2 inner product uv with the positive sign. 2 inner product of uv minus 2 inner product of uv will be cancelled, and we'll get 2 times norm of u square and 2 times norm of v square. So this will be true. So if you put a negative sign here, so your norm terms will be cancelled, and you will get 2 inner product of uv plus 2 u dot v. So which is 4 times u dot v. So 4 को divide करेंगे दूसरी side पे, so you will get this inequality. These two things will be proved in a very similar way. Just you have to put a negative here, and here you have a positive sign. This is the only difference in proving these two things. I hope you can do it. There are a couple of examples related to these properties. I hope you can see them. I'll advise the TA to solve the questions related to these inequalities or equations in tutorials, so that you can better understand these kind of inequalities and equations. If you have any question, you can ask me. Otherwise, we are going to stop it here today. In the next lecture, we shall start spanning sets and dimension and these kind of things.
Sir, are we expected to know the proofs for your test?
Test quiz?
Yeah.
Quiz 4, I think in the next week, I'll take.
So we're expected to know the proofs for that.
Yes. You should be able to prove these equations and inequalities. Any other question?